lines. Magnetic field lines are lines of force along which the magnetic force acts. Let us carry out a small experiment. We have here a surface which has iron filings on it. On this surface we place a bar magnet. We find that the filings arrange themselves around the magnet in a peculiar fashion. They form lines which extend from one pole of the magnet to the other. These lines are the magnetic field lines of the bar magnet. Magnetic field lines are continuous in nature. They do not end abruptly. These lines extend from the north pole to the south pole of the magnet. This is very different from electric dipoles. Electric dipoles may extend infinitely into space. Magnetic field lines, on the other hand, must end at a pole. Magnetic field lines are an indicator of the strength of a magnetic field. Stronger magnetic fields are characterized by a greater number of field lines than weaker magnets. Magnetic field lines are also denser in strong magnets when compared to weak magnets. Another unique property of magnetic field lines is that they never intersect each other. No matter how dense the field lines are, they never cross each other. Now that we've learnt about magnetic field lines, let us look at how they appear for different kinds of magnets. One such kind is a circular current-carrying loop. We know that currents have a magnetic field associated with them. Observe on the screen how the magnetic field of the current-carrying loop looks. Combining several such loops gives us a coil known as a solenoid. Notice how similar the magnetic field of the solenoid is to that of a bar magnet. We can now assume a bar magnet to be magnetically similar to a solenoid. Let us discuss this mathematically. Let us consider a solenoid having n turns per unit length and carrying a current I. Let its length be 2L and its radius be A. It is possible to evaluate the axial field of the loop at a point P, which is at a distance r, from the center O of the solenoid. In order to do this, let us consider a circular element of thickness dx in the solenoid and at a distance x from its center. The element dx contains n dx turns. We have learnt in earlier chapters as to how to calculate the magnetic field along the axis of a circular loop. At point P, the magnitude of the field is given by dB equals mu naught n dxi a square by 2r minus x square plus a square whole raised to 3 by 2. The magnitude of the entire field can be obtained by integrating this equation along the entire length of the solenoid, which extends from minus L to plus L. This gives us B equals mu naught n I a squared by 2 integral minus L to L1 by r minus x squared plus a squared whole raised to 3 by 2 dx. If we are to consider the far axial field of the solenoid, we find that r is much greater than both a and L. The denominator in our equation can then be approximated as r minus x whole squared plus a square whole raised to 3 by 2 equals r cubed. Substituting this in our equation for the magnetic field, we get B equals mu naught n I a squared by 2r cubed integral minus L to L dx, or B equal to mu naught n I by 2L a squared by r cube. Magnetic moment of a solenoid is given by the product of the number of turns of the solenoid, the current in it, and the cross-sectional area of the solenoid. Mathematically, m equals n into 2L into I into pi a squared. Substituting this in our equation for magnetic field, we get B equals mu naught by 4 pi into 2m by r cubed. This expression for the far axial field of a solenoid is the same as that for a bar magnet obtained experimentally. Thus, we can conclusively say that a solenoid behaves exactly like a bar magnet. The dipole in a uniform magnetic field. Even though the iron filings method for finding the field of a bar magnet gives us approximate values of B, sometimes greater precision is required in its measurement. In order to do this, we place a compass needle in the magnetic field and allow it to oscillate. The magnetic moment m and the moment of inertia I of the needle are known to us. The torque on the needle is given by tau equals m cross b. Magnitude of the torque would be tau equals mb sine theta. Tau here is the restoring torque. Theta is the angle between m and b. In equilibrium, therefore, we have id square theta by dt squared equals minus mb sine theta. When theta has extremely small values, we can approximate sine theta to be equal to theta. This gives us id square theta by dt squared is approximately equal to minus mb theta, or d square theta by dt squared equals minus mb by I into theta. This equation represents simple harmonic motion. The square of the angular frequency would be omega squared is equal to mb by I, and the time period would be t equals 2 pi root I by mb. Rearranging terms, we get B equals 4 pi square I by mt squared. The magnetic potential energy would be um equals integral tau theta d theta. This can be simplified as equals integral mb sine theta d theta, which is equal to minus mb cos theta, which is equal to minus m dot b. This equation means that the potential energy of the needle is minimum when it is inclined at 0 degrees with the field, and maximum when it is at 180 degrees with the field. Magnetic fields can be considered to be analogous with electric fields in some respects.